Dear guests, welcome to the second day of our symposium. We will start with session 3, which is quite an intensive session with 6 speakers. Each one of them will have approximately 20 minutes of speaking time. The topic here in this session is novel approaches in HVAC system design. Our first speaker is Mrs. Sinem Gündogdu Kalkın. She will be talking on energy efficient retrofitting in buildings, sector coupling and sustainability. I would like her to introduce herself a bit before her lecture, and the floor is yours, Mrs. Kalkın.
Hello, this is Sinem. Thank you for giving me the opportunity to speak about energy efficient retrofitting in building, sector coupling and sustainability today. I work for Danfoss as a Global Business Development Manager for sector coupling in climate solutions. And I hope what you will hear today will be impressive for you. And I think it will make sense that if I start sharing my screen now. Perfect. So as you can see from the screen, today's topic is to speak about energy efficient retrofitting in building, sector coupling and sustainability. First, we will discuss about the waste heat, the excess heat. What is it? What is the total potential of it? And then we will be discussing how we can use that waste heat with the sector coupling approach, how we can classify the waste heat based on the temperature ratings. And at the end of this session, we will be reviewing some examples from the industry that we had concluded as a project. When we talk about waste heat, excess heat, both means the same. In our company, when we first started this approach to prioritize this topic, we had noticed that the facts within the regions. And in Europe, we noticed the excess heat amounts around 2,800 terawatt hours, which is actually the equal amount of the requirement of heat and hot water for residential, commercial, and service buildings. So we basically use this, you don't use that source, and much of them are, instead of being captured and used, just rejected. So for this, there are several technologies exists. We had this initiative and created this web page, whyenergyefficiency.com, to explain the industry what can be done with that excess heat, either reusing it with the same entity or using sector coupling approach, designing smart urban planning, and also district energy. While we make our study, it was also important to understand the energy inputs. First of all, we understood how we are still relying on petroleum, coal, natural gas, all of these high CO2 emission sources. But then the interesting number came out, which is 72%. So the overall global energy input from them, the 72% of them are rejected. Of course, the future scenario looks much more better, where we are seeing the trend of using the renewable energy sources instead of petroleum, coal, and natural gas. We are also seeing that there is a trend on electrifying the heat and the cooling. And also there is a trend on focusing on the energy efficiency to avoid the waste heat. And also the flexibility. While we were thinking about all of these aspects, of course, these trends on choosing the type of the energy source or having this energy efficiency approach, it really depends on where you are based, which region that you are in. If you check the Nordic countries, you would see the trend more on this renewable energy sources side. If you would check countries like Germany, where I am based, we are basically more relied on geothermal. We used to rely on a lot on natural gas, but now coal. In France, you would see mostly nuclear. Mm-hmm. when we are discussing about this, we talked about electrifying the heat and cooling, but it all depends on the spark spread. This is the term that had been used in Europe quite a lot right now. So in order to invest on such technology to electrify the heat and cooling, we need to make sure that the electricity price is not slightly higher than the gas price. This map is created by European Heat Pump Association, where you can see it makes more sense to invest on a heat pump in Nordic countries, and also there is a trend ongoing in Central Europe as well. For that, I think it makes sense to not to focus on the gas price itself in current circumstances, because as many of you may be aware, in 2023, European Union had created this new energy efficiency directive, which is actually a base of new heating laws of all of these European countries. Germany had presented their heating law in January, and there will be a new heating law in Turkey as well in the following years, where in this heating laws, they are focusing on maybe an additional carbon tax when you are using these sources for the heating and cooling. And they are also giving responsibility to service providers to ensure that they have the source of waste heat as a base load when supplying the heat to the network. And also they are in these laws, they are also ensuring these high waste heat facilitators to ensure to recapture some of them, like data centers, hospitals, or 7-day, 24-hour active plants. So understanding the future investment only goes with the current facts, but also the future assumptions based on what is happening around the world. The term of sector coupling is quite important when considering reusing the heat or focusing on the waste heat. Actually, the meaning of the sector coupling is actually connecting different sectors like heating, cooling, and electricity. The main purpose is to create an integrated and more efficient system for production, distribution, and the use of energy. In this context, there are three topics that we are focusing. One is reduce energy, the other is reuse energy, the third is sourcing the green energy. By reducing energy, it is all about the optimizing the energy use when it is needed. For example, by implementing control systems that shut down the equipment and systems where they don't need. A simple retrofit actions like upgrading the current heating and cooling system with components, isolation. These would be all considered in reduce energy. By reusing the energy, our focus is in sector coupling is process heat recovery, where in one process the rejected heat can be used for another process or within the same process as a preliminary work. The best solution for it, if the excess heat amount is quite high, if it cannot be used within the facility, to supply that heat to district energy networks. This is quite an efficient way to focus when considering sector coupling. The third is, of course, sourcing the green energy is the use of renewable energy sources such as solar and wind power in the power grid, and ensuring that they are included in current industrial input. When we had started our journey as sector coupling team, we had created a lot of projects from different sectors, from different heat sources. These are the projects that we had worked in the last 2 years. We had a lot of opportunities for geothermal, process cooling, heat recovery, wastewater, and the other is actually data centers, which we see quite high opportunities. So the these are actually the temperature ratings that we see from the industry. How qualified would be that excess heat, what we can do with that excess heat actually comes from this experience. We noticed that when designing a sector coupling project or focusing on the excess heat, it is really important to classify who would be the source, who would be the demand, and what would be the technology that they use. And for that, we need to make sure that the temperature ratings are classified in a specific way. So for that, we have used the classification as low temperature source, medium temperature source, and high temperature source. Based on this experience, this is just a simple project that we had done in Warsaw Metro, where we had recovered the heat from the exhaust of the metro station. And then we had this heat recovery station to ensure that we are supplying the exact heat that would be required for a heat pump. And then we also integrated with a heat storage just to ensure that when district energy requires the heat, gets it in the certain temperatures, and also when they don't need, we can storage it. When they need it much more than what we can supply, we can use the one that we had stored previously. For that, just like I said, it is important to understand who would be the source, who would be the demand, and what sort of technology that I will use in between. Considering this experience, you can see a number of examples, including the temperature ratings. So let's say if we have a subway exhaust recovery, we would be thinking about the temperatures around 15 to 35 degrees. And if we select a district heating network to supply that heating, of course, for this district heating network, the example is fourth generation. Just a quick information, district heating networks are divided by different generations. So if it is fifth generation, they are requiring less than 50 degrees for supplying the grid. If it is fourth generation, it's between 50 to 80, which is how Nordic countries had been using. And there is also third generation of district heating, where countries like Germany, which depending on the state, we may require 90 degrees or up to 120 degrees. This is called third generation district heating. Coming back to the topic. So if we want to supply that excess heat from a subway system to a fourth generation district heating network, we would need around 65, 67 degrees. So for that temperature rating, what do we need? Of course, we need a heat pump because we need to boost the temperature. Because the temperatures are okay, less than 75 degrees, it is possible to use oil-free compressors, which has the centrifugal compressors and are quite efficient. We can just supply it to district heating network, supply the waste heat from subway to district heating network. Another example would be a wastewater, which we have quite experienced, especially in Germany and Denmark. If we want to connect it to district heating network, again, we would need a heat pump. Same goes for data center as well. If we have a greenhouse, which we selected as a demand for from the data center to use the excess heat, we don't need a heat pump because we don't need to boost the temperature. We just need a heat recovery station just to ensure that we are providing the right amount of level of temperature to this greenhouses. Same goes if we would like to supply the excess heat from a data center to a brewery, then we would need, again, a heat pump. But this time, because we are requiring much higher temperatures, over 80 degrees, we may need to select a heat pump with a piston-based compressor. These examples are not really focused on only data centers, subways, or wastewater. There is also process heating and cooling applications. For example, if we have a paint oven in such a facility, we would like to recover that heat within the same facility for process wash water. We may need, again, a heat pump to boost the temperature for the requirement. And it would be a good example to use the sector coupling approach within the same facility. Same goes for biofuels or plastic extrusion. Based on our experience, we had designed systems from 300 kilowatts to 60 megawatts. And in that experience, this is the graph based on all of these accumulated by all of the projects that we have dealt with. So for each 1K differential, we had seen that the heat pump efficiency increases 2%. And when we are speaking only about efficiency, it is really important to ensure that if you are invested on a heat pump, you have the right amount of COP in that heat pump. So when we have talked about waste heat. Then we had talked about, how to classify the heats, low, medium, high. And then we had decided a technology, let's say a heat pump or heat recovery station or heat exchanger itself. Then we need to ensure that we have the right differential. If there is a possibility to reduce the temperature from the demand side or to reduce the overall temperature from the demand side or increase the temperature from the source side. Let's start with a couple of examples, and I think it will make more sense how we had designed all of these systems. This was one of the projects that we had worked for Hamburg Wastewater. There we had invested on a heat exchanger to ensure that we returned the correct amount, level of temperature to the wastewater facility. And then we had connected to a heat pump and then to a heat storage to the fourth generation district heating network. The positive side in this project was because the temperatures were less than 75 degrees, we had the chance to use the oil-free technology, which is for efficiency side much better than piston compressors. Those are quite compact, so very small size by the appearance, but for the capacity you can reach up to 1,000 kilowatt in single compressor. And also because it's oil free, the system is much simple. You don't need the filter, you don't need the oil cooler. It's much more simple system, and those are reliable systems. Even after 10 years, you would still get similar efficiency from that compressors. So in these overall system, it was possible to reject that heat or reuse that heat in a district energy network, where it was a quite sustainable experience from us. Another example was from a data center. In this example, we had worked with a data center that has direct on-chip cooling. We had connected it with a heat recovery station and then to a heat pump, then to a heat storage and accumulator tank to district energy network. The cool thing in this project was it was possible to manipulate the temperature in a heat recovery station to get a free cooling in the data center. Because the heat pump was providing much less temperature than required in the data center to the heat recovery station. Obviously, this was a good experience because in data center, we had this direct on-chip cooling. So there are new technologies. This is on-chip cooling, but before and in some countries still there is a possibility to have air-cooled data centers where they need 15 to 20 degrees, which is not really allowing to have higher efficiency on the heat pump, because eventually if you need to still deliver 6 or 7 degrees to district energy network, and if you need 20 degrees rather than 30 degrees in your data center, of course, the delta T in heat pump is going to increase. And of course, the COP is going to decrease. Just one quick note about this example is this heat recovery station is quite actively used throughout the Europe and also in the US, where it is just a container size and the minimum, the capacity is 5.5 megawatt. And it's quite attractive for data centers because they are not really into this heat recovery topic, where even though in this new energy efficiency directive, they have this obligation to recover the heat if they are creating the waste heat in a certain amount. But it all depends on the power usage efficiency of the data center. And if it is around 1.2, they don't even need to invest on such thing. But with the new laws, they have to focus on this topic. And also district energy network companies also have to focus on this topic. Another example, which I explained a little earlier. So from a data center, I can recover heat to a greenhouse, where in greenhouse, I would need only 25 degrees. So I don't need a heat pump because I'm not requiring a higher temperature. With a heat recovery station, I can easily use it in a greenhouse just with a heat recovery station. And it would be a great example. One note is right now, some of the data centers have been making deals with the manufacturers. For example, Iron Mountain has a deal with a salmon manufacturer, not only greenhouse, but indoor fish production. They would also need such lower temperatures. So wherever Iron Mountain is establishing a new data center, this salmon manufacturer builds a facility right next to it, and they simply connect with the pipes and get the free heating for their manufacturing. It is quite a good system because if the distance is around 1 to 1.5 kilometer, you can still get a good temperature rating from between those two facilities. Another example, just I explained in the previous slides, we can easily boost the temperature for a requirement in a brewery. And again, for this example, we have used to recover the heat from a data center. There was one other example which I couldn't share in these slides. This was a project for a residential building in New York, where the building was a 30-story building. In the 15th floor, we had this data center, and they had the waste heat amount of 6 megawatt, where we had in the past, all of the other stories had the connection with the district heating network. But right now, with the system that we had designed, all of the building gets the heating for free from the data center. Of course, for free, I mean, for the source, they don't have to pay, but for certain technology, they have to pay. Just a quick note, of course, there are millions of ways to make a system efficient on the energy side, but also it depends on the price as well. So we have to search for the most optimum solution for each case. That's why each case has to be tailored at some point. When we are talking about these sort of projects, we are talking about the return on investment between 2 to 5 years, which is quite attractive based on the overall economic circumstances. This was another project that we had done. They had this extrusion process for the aluminum parts that they have been producing in one of the customers. So we had installed a containerized water-to-water heat pump, where we use this rejected heat in the parts washing process of the same facility. So overall, what I try to say is it is quite important to focus on the topic of waste heat to ensure the reduce the waste heat by making certain upgrades. It can be a component or a simple isolation project in such a project, and then reuse the waste heat. So it can either be upgrading the current heating and cooling system, like from boiler to a heat pump, or also it can be a way to use that rejected heat from one process to another. And if possible, a district heating network. So in some countries, we don't have district heating network, but we have these local approaches. Like in Ireland, there is no district heating network. Of course, there's a trend now, there will be in the future, but we have these industrial zones where we share this rejected heat in between the facilities. And it's a really quite simple system. And right now, with these new financial support, of course, again, using the green energy, renewable energy as a main source, it will help us to reduce the CO2 emissions. Apart from this, just to remind again, it is important to understand what do we mean by source, what do we mean by demand, how to classify the temperatures, and how to select the overall technology. We have a lot of examples, a lot of case studies. This was the last slide of my presentation. I'm unsure if we will have time for questions, but if you have any questions, my name, contact detail, my name is already in the web page. You can connect with the LinkedIn, and it is easy to reach out our case studies from our websites. Thank you for giving me the opportunity and for this organization.
We thank you, Mrs. Kalkın, for this. At least for me, it was a wonderful presentation, a bird's eye view of this domain. And sector coupling is a very interesting wording, actually. I usually think of old times when tailors used to leave a bow, and when they come downstairs, they used to work all day long. So this is a wonderful way of making the society efficient. And this time you spoke about the industrial perspective of it. I'm sure I will forward my students, my fellow students, to you, to your addresses. And I think whyenergyefficiency.com would give some examples from.
Exactly.
Okay, case examples.
Yeah.
Okay, thank you very much once again.
Thank you.
I would like to continue with our second speaker of the day, who is Emre Özmen. He's far away. He's in Japan, as far as I know. I would like him to introduce himself a bit, and the floor is yours, Mr. Özmen.
Thank you, Mr. Chair. Sorry for my background. I have a technical problem, first of all. It's all my fault.
No problem.
This is Emre Özmen. I have graduated from Technical University of Istanbul Mechanical Engineering branch in 1994.
Emre, I'm sorry to cut you. Could you bring your microphone a bit closer, or is it possible to come closer to your PC or something? Because I have a hard time hearing you.
Is it okay now?
Better. Okay, thank you. Go ahead, please.
Okay. Thank you, Mr. Chair. Hello, everybody. And this is Emre Özmen. I have graduated from Technical University of Istanbul Mechanical Engineering Department in 1994, and in 1997 from robotics, and I completed my Master of Science degree from Istanbul Technical University. And for the last 30 years, I have been working as an engineer in the building sector, and as a consultant, designer, and also third-party commissioning authority. And thanks a lot for coming and listening. And I will share my screen. Thank you. Yes. Okay. HVAC system commissioning process in data centers. I have 20 minutes and I have a lot to talk, but I will try to do my best in order to fit the time frame. And the goals of this presentation is talk a little bit about commissioning, data center commissioning, HVAC system commissioning benefits, HVAC system commissioning scope, commissioning process, standards and guidelines, and facts and figures. What is commissioning? According to ASHRAE standard 202 2018, it is a quality-focused process for enhancing the delivery of a project. It focuses on verifying and documenting all the systems and assemblies in the data center if they had been done as planned, designed, installed, tested, operated, and maintained. So what do we have as a HVAC system in a data center? Here we can talk. Let me get to the laser pointer. Yes, when you will look here, you can see all the data center physical infrastructure here. I have deliberately put this because I wanted you to see the whole picture of the infrastructure. But our topic today is the HVAC system. And we're talking about primarily the cooling system because the main problem with the data center is the cooling system, of course. So the chillers, cooling towers, economizers, liquid cooling cycles, or of course the pipelines, the circulation pumps, valves, thermal storage, heat exchangers, recovery units, computer room air conditioner or computer room air handlers, direct expansion air handling units, and of course the airflow management, the raised floor, ductwork, and rack containment, the hot ale, cold ale. So when we're talking about the HVAC system commissioning, we're taking into consideration of these systems. There is a technical committee. It's famous globally. It's ASHRAE Technical Committee 9.1. Mission critical facilities, data centers, technology spaces, and electronic equipment. The name of the technical committee is this one. It's one of the most crowded technical committee of ASHRAE globally. And according to their definition, data center is a room or building or portions thereof with one or more IT equipment enclosure greater than 2 kilowatts. And the information technology equipment, what are those? Those are computers, data storage servers and networks, and the communication equipment. So nowadays we're living in a very, very, interesting digital world. The emerging services and technologies all of us are hearing frequently: streaming, cloud gaming, blockchain, artificial intelligence, machine learning, and virtual reality. Those are really, really boosting the demand for data services. Everybody is hearing the ChatGPT and the others, all the people, they are trying to use it in their, professions or in their, normal life for their curiosity. So nowadays the demand is booming. So let's come to the commissioning benefits. What do you have when you do the proper type of commissioning in the right way if you to your HVAC system, the data center? First of all, the commissioning improves the occupant comfort. Of course, there are the facility team in the data center. Then the operational reliability and high uptime. That is one of the most important things for a data center to earn money. So the third one is indoor air environmental quality for either for IT equipment in order to prevent the corrosion, or the people are working there. And data center physical security, it's very important. And of course, occupant productivity, data center service equipment life, and data center systems maintainability, and the DC, the data center energy performance, facility management team efficiency, and technical documentation. And another benefit can be talked under the quality-focused process. What do we do? The commissioning prevents the technical problems. And of course, designers focus on the owner needs according to the owner project requirements. And when they do that, they easily address design issues early in design, they improve technical specification, and this reduces the request for informations and change orders. And of course, lesson learned opportunity for designers. It's very important for them for their next design. If we continue for the quality-focused process, contractors focus on the owner requirements. This improves submittal process, and of course, the timely delivery of operation and maintenance materials, efficient training sessions, address deficiencies at the start of the installation, and the test finished work to verify performance, and document all testing activity, and building projects can be completed on time. This is very important because, especially in our country, the building projects, the data centers, of course, they are having difficulty to complete on time. And the commissioning addresses deficiencies and it gets remedial action taken. What are those? The design issues we talked, and the failed or over-undersized equipment system, installation issues, improper tuned controls, improper control sequences, poor testing, adjusting, balancing works, redundancy problems, insufficient training, insufficient technical documentation, and high PUE, the unsatisfactory energy efficiency. And also, commissioning sets clear, measurable technical goals for every discipline. It verifies the milestones are being reached throughout the CX phases, commissioning phases. Data center projects can be completed on time. Data center projects can earn tier certification. For example, Uptime Institute. Reliability means reputation. Reputation means money. Data center projects can earn sustainability certification. It's again, reliability for reputation, for LEED, for example, BREEAM. High energy performance means that ideal value of PUE, which is 1. So high energy performance, you can go to as low as you can to 1 as PUE value. Low carbon footprint, of course. And also commissioning brings accountability, open book, commissioning management software you can use, and it changes the way people perform. You can watch everybody's activity. Everybody can watch everybody. So allows contractors to measure success as well as deficiency, and acceptance process becomes more transparent. And of course, there is less conflict between disciplines. When we come to the commissioning process, the first phase is pre-design. At the pre-design phase, the owner hires the CX authority, commissioning authority, and also the design team. And also the commissioning plan is prepared by the commissioning authority. It's very important. And this plan, it's as an initial plan, of course, it should be changed in the future phases. But this is very important. The commissioning plan should be prepared at the pre-design phase. It's very early of the project. The second phase is, of course, design. It's very important. Design team or design office is hired already. They start to develop the basis of design document, then the design package, then the construction project package. And of course, the commissioning authority reviews all these products and reports to the owner. And then the design package is released and the tender is opened. And of course, during this period, the commissioning meetings are organized and held by commissioning authority. And the third one is the busiest one, is the construction. You can tell that there are 5 levels. The first level would be factory acceptance test. The second one would be the equipment acceptance. I mean, do we get what we have ordered? the commissioning authority just checks all the incoming material to the site, and also checks the storage conditions, and of course the installation qualification with the control checklists. If there are some deficiencies, they will be closed out according to the owner demand, and then you move to the L3. Level 3 means startup and testing adjustment balancing. So there are some procedures, and the commissioning agent witnesses the tests and manages the tests, and the general contractor and the subcontractors, they just execute the tests. And if there are some deficiencies found, the same story, they can be closed out according to the owner demand. After that, the level 4 is coming, which means the functional performance testing. All the HVAC systems and equipments, they are tested according to the tailor-made test procedures by the which are developed by the commissioning authority. And of course, the general contractor and the subs, they execute the tests, and the deficiencies found, if there are any, so they can be closed out. The most important part is the L5 integrated system testing, because we talk all about the more efficient and more resilient data centers, high uptime. So this L5 integrated testing is very important, because in this test, it's all the systems interact to each other, and you just do some stress tests, and those tests ensure that the redundant components, the systems, and the interrelated systems, they are tested for their response as the owner project requirement. For example, you can just shut off the mains electricity, then you shut on again, and you just watch for the reaction of the whole electromechanical system. This is very important. That is a hands-off test, and you are expecting that the system will come back without any problem as soon as possible. So that proves the reliability of the data center, and this is also certificated by some certification bodies like Uptime Institute. Of course, in this phase, I shouldn't forget to share with you the operation and maintenance documents should be reviewed, and training activities are also evaluated and reported to owner. And the last one, the occupancy, last phase, fourth phase, the as-built documentation are submitted by the GC, general contractor, and they are reviewed at the office by the commissioning authority. Seasonal tests can be done for fine-tuning. The feedback of the facility team, it's very important. The commissioning agent listens to them in order to do some fine-tuning during the warranty period. Warranty review is very important. The commissioning authority will ensure that any operational issues under warranty are identified and addressed by the contractor before the warranty period expires. And of course, lesson learned workshop and final commissioning report. And after the new building commissioning process, data center commissioning process finished, the ongoing commissioning activity can be done by facility till the end of the data center lifetime, or they can hire a third-party commissioning authority also. And this is a process key aspect. I don't have too much time, so I will skip this. If anybody interested in this, they can just check it out. I will share the presentation. And when we talk about the ASHRAE standards or international standards, we can talk about the guideline 0 and standard 202, ASHRAE standard 202. And also there is another guideline, ASHRAE guideline 1.6, commissioning of data centers, which is pending. The ASHRAE is still working on that. This is the purpose and the scope of this guideline. It is for new and existing data centers, not for data equipment networks. And the guideline will include the following sections. The interesting thing, there will be a load bank plan, and of course the FAT plan, The others are nearly same with the standard building commissioning. And when we talk about the data center energy and carbon footprint, let's talk about some figures very quickly. The International Energy Agency stated that the total global electric consumption of the world, if it is 100%, the data centers are responsible for 1 to 1.5% of that. And this figure is before the ChatGPT or artificial intelligence. After that, according to Goldman Sachs, they think that the power demand will grow by 160% till 2030. And also till 2030, the carbon footprint, the metric tons of carbon dioxide would be 2.5 billion metric tons, which is huge. Another one from IEA, they say that the data centers and data transmission networks that underpin digitalization accounted for around 330 million ton carbon dioxide equivalent in 2020, which is equivalent of nearly 1% of the energy-related greenhouse gas emissions of the world. The last two slides, data center energy use increase in the last 7 years. You see that it is between 20% and 70%. And if you include the crypto mining energy use, it is 2,300 and 3,500% increase. This is huge. When you go for the PUE, it is, the standard efficiency metric for power consumption in data centers. So the green grid calls it as power usage effectiveness. From the year 2007 till up to today, you see it just decreased a little bit, but it started again increase slightly, which means that everybody needs commissioning. So commissioning services encompass and enhance all measures if applied properly. So the last thing I would like to share with you guys, here you see the blue. It is 14%, which represents the cooling system that causes the significant shutdown of data centers according to Uptime Annual Survey 2021. So which means cooling is one of the important segments of the successful DC operation. So the commissioning of the cooling system is very important. The last thing, last slide, the renewable energy power purchase is also very common in the sector. The big players, they reduce their environmental impact and they want to improve their brand reputation. So they try to buy renewable energy, or they just run their renewable energy sources. So if you look at here, they just between the last 12 years, from 2010 to 2022, these guys, Amazon, Meta, Microsoft, and Google, they bought a lot and they just invest on renewable energy power purchase. Thank you for your attention.
Thank you very much, Mr. Emre Özmen, for this informative talk on commissioning of data centers and specifically speaking on data center cooling. In the back of my mind, I have two figures which I use in my teaching. In 2022, the data center electricity consumption was around 500 terawatt hours. In 2026, in 2 years from now, it will increase up to 1,000 terawatt hours. So, of course, the cause is very evident. The causes are very evident, very clear. AI and crypto mining, plus the data transmission, of course. So,
yeah.
In the future, these domains are quite virgin fields for us engineers in terms of cooling. We need to design and function, make active systems with clever applications and so on and so forth, so that the DC consumption, cooling consumption, somehow is maintained quite rationally. Okay, thank you very much once again. And now with this, we will pass to our third speaker, Professor Ahmet Arısoy, who will talk about performance of hybrid cooling system for different climates. I think everybody knows him from academia, from his invaluable work in TTMD and other things. But of course, he will probably spare a few words to introduce himself before his speech. Dear Professor, the floor is yours.
Okay. Thank you, Murat. Thank you, dear Chairman. I'm going to talk about an innovative approach to cool the buildings, and it will be very much related with the ZEP, zero emission buildings. Okay, then let me share my screen. Okay. But I had to go back. Okay. Now, okay. The title of the study is Performance of the Hybrid Cooling System for Different Climates. We talked about this system before, and I will not give the details of the system, but I will give in this presentation the performance of the system to give an idea how this functions, how this operates, and what is the advantages, and would it be a solution for ZEP. All we know that as a result of global warming, the need for cooling is increasing. The increasing level of welfare and population growth are also acting in the same way. So therefore, the trend is now more energy use for cooling purposes in the coming years. The second fact is, on the other hand, it is aimed to reduce the fossil fuel-based energy used in buildings all over the world, and the eventual target is to make it zero. And actually, we shifted from energy to emissions. Then instead of zero energy buildings, now we talking about zero emission buildings. In Euro, ZEP standard will replace present standards in 2030. So zero emission buildings brings the rule of zero carbon emission from the buildings. So the main target is not energy now, it is emission. This zero emission buildings, in this zero emission buildings, the entire energy consumption is met by renewable energy. We shouldn't emit any carbon. So in terms of cooling, electricity energy consumption in cooling systems should be minimized. So we have a problem, we have a target. In these circumstances, it is necessary today to develop innovative low carbon cooling systems to achieve this ZEP goal. An innovative hybrid cooler is introduced in this study. There are no surface heat exchangers are used in the solution. The air is washed directly by the chill water. Actually, most of the time, only evaporative cooling of the air and the circulating water is sufficient, depending on the outdoor weather conditions. In extreme conditions, a chiller is needed to cool further the circulating water. It is important to know the energy consumption of the cooling system during the entire cooling season. If you would like to calculate or see the performance of the system, we need to consider entire cooling season. So seasonal performance of the system depends on changing outdoor air conditions. To calculate this seasonal energy consumption, hourly cooling loads of the considered building should firstly be determined. Then second stage is calculation of the electrical energy consumption of the defined system to provide the calculated cooling load. To demonstrate the performance of the proposed hybrid cooling system, this office building was considered, and 8 sample stees from different regions of the Turkey are taken into account to cover different climatic conditions. Selection of the design indoor condition is very important. It is crucial for the performance of the system. In this case study, indoor design condition is selected as 24 degrees Celsius, dry bulb temperature, and 62% relative humidity. With this defined design indoor condition, washing water temperature should be fixed through entire season at 17 degrees Celsius. If the outdoor weather bulb temperature is below this fixed temperature, I mean 17 degrees Celsius, only evaporative cooling will be sufficient to cool the building. Otherwise, chiller will be activated to support the cooling process. The calculations are repeated for the conventional all-air VAV cooling system to compare. Results of the calculations are given in the full paper. I'm just going to give only Ankara and Istanbul here. Main electrical energy consuming equipment is fan and compressor of the chiller in both compared cases. Pump also consumes energy in hybrid cooling case. Fan, pump, and chiller efficiencies and their energy consumptions are varying depending on the cooling load. This should be considered. I mean, this part load performance should be considered in the calculations. For these eight STs, total electricity consumptions were calculated for both cases, and dividing this electricity consumption to total cooling load, seasonal energy efficiency ratio, CER, were determined. So we have to look at this value, CER value, because it is the best indicator of the performance. If you look at the Ankara results, Ankara is an inland city at the middle of the Turkey, and climate is dry in summer, so it can be considered as favorable for evaporative cooling. All the above mentioned performance values calculated for Ankara, and it is given in this table. First thing is this cooling load. It is same for both cases, naturally. And if we look at the total energy consumptions, electricity consumptions actually, there is a big difference between these two cases. If it is this proposed new hybrid cooler, it is approximately 1,000 kilowatt hour during the entire season, cooling season, but it is almost 8,000 kilowatt hour for conventional cooler. From this, the CER value is 4.9 for conventional solutions, and it is 27.7 for new proposed system. As can we see from these values, there is a big difference between CER values, and this solution is a perfect solution for ZEP, let's say in Ankara. If we look at the working modes of the proposed system, there are three working modes: operating cooling only mode. As we see, it is the biggest part of the, these are the hours during the whole season. As we see, system works on only evaporative cooling mode most of the season, and almost half of the time of this time it works on hybrid cooling mode. Only a small fraction of the time it works only mechanical cooling. In that time, system works only based on the chiller. So if you look at the Istanbul, in this case, the Istanbul is a coastal city at the northwest of the Turkey, and climate is mild in summer. Outdoor conditions in Istanbul can be considered not good for evaporative cooling. However, still hybrid system has better performance comparing the mechanical system. As we look at the results, conventional cooler CER value is 2.65, but it is 3 for this proposed new hybrid system. There is a meaningful difference between these two systems, even in Istanbul. So if we come to conclusions, we need increasing cooling need due to both global warming and the increase in people's welfare. And so we need to develop new cooling systems which require very small amount of electrical energy that can be provided by renewable sources. In this presentation, such a system is proposed. This system can provide a solution for ZEP, zero emission buildings in convenient climates. 8 different cities of the Turkey from different climatic zones are considered in this article, but the calculated CER values for dry inland cities are very high and this proposed system can be a very good solution for Z in such climates. Thank you for listening me.
Thank you, dear professor. Thank you very much. Actually, evaporative cooling is to me at least, evaporative cooling is a neglected area, especially in some parts of Turkey. Your presentation actually showed this reality, that it can be used to arrive at zero emission or zero energy buildings. Both are applicable in some parts of our country, and this should be a nice attempt for researchers or for companies for the future. Thank you very much once again for your very informative presentation. Now, this brings us to the presentation of Mr. Alper Üzmezler. His title of his presentation's title is Project Sandstar. Mr. Üzmezler, we are looking forward to hearing you about this project. The floor is yours.
Thank you so much. All right, so my name is Alper Üzmezler. I'm the founder of Project Sandstar. Basically, Project Sandstar enables and changes the paradigm for smart building space, and it enables hardware agnostic controls that is open source. So the slogan for Project Sandstar is VIoT is greater than 5. There is only certain, there are like 5 large companies that are basically dominating the market. And in order to change that, we have created, we are creating an association within Turkey. And basically, the current state of affairs for smart buildings is that each hardware manufacturer builds hardware and they write a software that creates a certain file or basically programs the device, PLC device via their written software. That basically restricts the market. When you want to move between different manufacturers, you have to redo the work that you have done within the application. So what we have done is we merged 2 open source technologies together where it enables hardware agnostic controls that is fully open source. So the problem is building systems are proprietary and they're built on old technologies. And the solution is hardware agnostic controls that is open source and also that is basically available for any manufacturer. So how did we achieve this? We achieved this by merging 2 open source technologies. One of them is called Project Haystack. Haystack is a semantic data model for Internet of Things, and it also has predetermined REST APIs built into it. Sedona framework was written 7 years prior to Project Haystack. It is a controls engine that can be installed in restricted hardware spaces to control inputs and outputs. What we have done is we basically abstracted the I/O information that are on electronic boards that are certain standards like I2C, UART, GPIO. We abstracted those with Haystack tags, and we created a Sandstar engine. The Sandstar engine is basically able to communicate to electronics board. But when you get to the control block programming level, you don't tell it is a binary output 1 like within BACnet. What we actually say it is a discharge fan command. That way, it basically abstracts the data on what you're controlling into a humanly understandable level, and it enables the logic to be ported between different manufacturers. So what does this enable? It enables us to basically generate value automatically because it is semantically data typed. You can have mobile apps, dashboards, we also open source a lot of these things, and we have a goal of bringing LLMs, and LLMs, basically artificial intelligence, into play as well in order to question the whole system. Hardware. So this is basically proof of concept of getting this working. We work with two different companies, two different CPUs, and we were able to pass the configuration file between two different manufacturers, and we basically literally achieved hardware agnostic controls. So the one on the left, it's built by manufactured by Solidyne Incorporated. The one on the right is based on Raspberry Pi. The one on the left is based on BeagleBone. These devices are open devices that have Linux on them. The hardware is open as well. So anyone that has the will to be in the smart buildings industry, the whole stack is available for them in order to achieve this kind of controls. And it basically liberates the market. The consumers of these devices, being spaces, they can choose whichever hardware is applicable for their application for controlling cooling or heating or maintaining certain things. Application stack is basically changes the paradigm. Existing systems are, even today, we are still utilizing serial ports. Serial communications like BACnet, MSTP, Modbus RTU. We have gateways, and the gateways, we collect them into what we call supervisors, and then we collect that data in all the way up to the cloud for analytics. This is a lot of data moving, pushing northbound. With these new level of hardware, where we have a lot of CPU and memory, and they're open source, we can actually combine that whole stack at the edge. So we can do edge analytics and control systems within the edge. So we're basically, what we are creating is exactly that. The data flow is basically, you can control your I/O with Sandstar. Sandstar basically abstracts everything out to web service via open source projects, Haystack. Within the same device, we can historize the data. So you can basically look at the data on an abstracted level. So your room temperature, zone air temp sensor, your fan is discharge air fan commands or status. So you historize all those, and you can analyze the system right within the devices as well. This system has a WebSocket clustering technology, and you can basically create a distributed computing within this model. So having a hardware, more CPU space with open source technologies is very crucial. What are things that we have achieved? We have open sourced the whole stack for indoor air quality sensor. So we have a Raspberry, we have a BeagleBone, a hat on a BeagleBone that is completely open source. Anyone can take this and compile it and install it and manufacture it. The only part is we get the indoor air quality sensor out of China that is very low cost, but anyone can build this indoor air quality sensor for temperature, humidity, and the data is trended. The data is stored right within the device. So you don't need to pay for software as a service just to collect data from these systems. Data flow explained, basically it is distributed computing. So if you have a rooftop unit and a VAV box and an indoor air quality, the part that we need is we need to basically look at the data from all, and we need to reset our systems, slow it down to save energy, or speed it up to improve indoor air quality. So in order to achieve this, we used to basically send the data from RS-45 devices to a gateway to a supervisor. Within this model, everything is flattened, and the controller, within the controller, you can actually question the whole network and find the value that is important for you to do your improvements to this whole overall system. Things that we have done is we have installed one of rooftop units in Florida. It has been running more than 6 years. That is just to prove that a proof of concept that can be achieved with open source technologies is available. What you're seeing here on the left is the historical data, and what you're seeing in the middle is visual tech that is also open source that creates user interfaces. Basically, everything that you see here, most of the stuff that you see here is open source. So Sandstar, block programming with haystack-based semantic data model, Visualitic to create user interfaces. All of those are open source. Mobilitic is a mobile app that is written in Project Haystack. It can communicate to a Haystack server. Within this case, we are communicating to the SkySpark server within these devices. But the application is open source. So Sandstar is open source. It communicates Haystack out, and then the Mobilitic is a Haystack client, and you can basically see all your sites, all your equipment, all your data via Haystack really easily right on your phone. So pilots that we have completed airflow monitoring for a university for 13 devices. Rooftop unit, we have done a rooftop unit VAV combination where it needed resets of 6 rooftop units, 26 VAVs, and air quality monitoring for various off-sites. So what we found is we can improve implementation costs by 25% by utilizing a semantic data model within the implementation phase of the system. So any hardware manufacturer, they can be a part of the Project Sandstar Association and get the stack of the code, and they can start building these and installing these. Energy savings is over 25%, depending on if the system already has a building automation system or DDC controls. If they don't have it, it will be probably a lot higher than this. So we have technologies used. We have utilized BeagleBone. We work with contemporary controls with their Raspberry Pi. Raspberry Pi is an open source Linux box. We work with Solidyne, where they're using Beagle boards, and most of these technologies are pretty much open source. So finally, stay tuned for the creation of Project Sandstar Association for an open feature. And if you have any questions, you can contact me on my LinkedIn. And finally, BIoT is greater than 5. Thank you.
Thank you very much, Mr. Üzmezler. Your presentation showed us the coupling of information technologies with the real applications of climatization. Let me ask you one thing. Is this association a profit-free association?
Yes, we will form a Derneği as an association within Turkey, and it will be non-profit. It will have programmers within the association, but it will be non-profit.
Okay, this is a very valuable information you give. Thank you once again.
Thank you.
I wish you success in your deeds. Actually, now it's time for our 5th speaker. However, just a second, please. Mr. Munish Digra, just 5 minutes ago, asked his send us his excuses, and I think he had an emergency and hospitalization or something like this. Of course, health is more important than any other thing. Therefore, we will decide whether we will ask our sixth speaker to the stage. Let me just okay, Mr. Galatioto and Mr. Demirdöven, if they are available, if they are ready, they can join us. Otherwise, we will approximately wait half an hour, and we will start the last presentation of this session at around 10 to 3 o'clock, 3 p.m. Just wait a second, and perhaps we will receive a positive answer from Mr. Galatioto. Okay, it seems like they are not online. So I would assume we would start our session back again at 10 to 3. And since then, please forgive us for this inconvenience. But of course, as I said before, health is an important thing. So we wait about a half an hour for the last presentation of the session. See you then. Dear guests, welcome to the last speech of session 3. This time we have just a second, please. Yes, a topic entitled as Energy Efficient Building with Filterless Air Pollution Abatement Solution. This speech is going to be given by Signor Galatioto and Mr. Demirdöven. The floor is yours.
Thank you very much, and thank you for the invitation. I'm going to share my screen, if that is now clear. And I'm Dr. Fabio Galatioto, I'm CTO of the HVAC&R Global Solution. And we have today the presentation of this work we have done last year, energy efficient building with filterless air pollution abatement solution. This project has been developed as part of an Innovate UK UK-based project funded by the government. And we have actually tried with this project to demonstrate the improvements in the heating and ventilation and air conditioning systems that can be done through alternative and additional technologies that are also sustainable. As an introduction, I have to say that 60% of the energy used in building is coming from this source of energy consumption, and they are still mainly relying on inefficient and expensive filters. These basically create an high cost, high energy use, but also a lot of maintenance and material use for the filter change. And so we have been asked to test the technology developed by HVAC&R as part of the objectives to reduce the energy consumption of the HVAC, monitoring the before and after, to enhance the existing system, also to make not just a reduction in energy, but also a reduction in pollution. And that will have the benefit for the human being occupying the office and the buildings, but also the overall reduction of cost in terms of HVAC system within the building. And finally, since the technology that we use is water-based, the idea was most of the air conditioning system tend to generate as a condensation the water during their functionalities. So checking also how much that was feasible to reuse the water as an additional sustainable metric. The reason why we wanted to focus on this option and this opportunity was also the cost associated with that. In particular, in just the UK, there are over 1.6 million non-domestic buildings. They are consuming overall 140 terawatt hour in a year, and equivalent to 30 billion, depending on the cost of the energy, of course. But this actually bill comes mainly from factories, offices, and warehouses, so building use, and 60% of that, so that means 30% of the overall energy, is associated with the HVAC systems. And our solution potentially was planned to be tested to reduce 20% the energy consumption, which overall, as a simple math, we can say it can save up to 1.8 billion, which is a big number, of course, assuming everything was converted into the integration of the system with the existing HVAC. On top of that energy element, there is, of course, the benefit of reduced maintenance, because our system basically improve the performance of the filters, keep them clean, and that means the building occupant and the tenants can save money overall, not just on the energy, but also on the maintenance side. And finally, in terms of air pollution, it is well known that air pollution in the long term can cause health disease, health problem, which are impacting the social cost. Just in the UK, an estimated of 23 billion annually, but also the improvement in workplace productivity, the better quality can generate much more performing, just simply not being ill for a virus that makes your employee more efficient. And that has been estimated to up to almost 6,000 euro per worker per year in a multi-decade study done in the US. In terms of the technology and what we have used, this is just a simple shot in terms of what can be used and what we have used. Actually, is the APA panel, which is in the middle left. And the principle is that the technology uses simple water, is an enhanced scrubber, which is also able to be reduced in size, to be used indoor, as well as outdoor, like the case we are presenting today. And there is also an element of decarbonization, because there is a CO2 component that can be removed at the same time. And it's a completely no filter. So the demo site we have chosen was an office already built in with existing HVAC systems. And you can see there were 4 slots of HVAC already in place. And we have deployed 2 of the APA panel systems, which will be, as you can see on the right, were deployed very close to the system. The reason we didn't deploy attached completely or connected directly into that, like a sort of enclosed system, is because this was a demonstration project and we needed to make sure that the maintenance service and everything that was associated with the insurance on the HVAC was not compromised. And that was enabling us to make the demonstration as well. So, of course, there were some limitations, but we were able to demonstrate the full effect. And also, in terms of monitoring, we have made sure that the different sections in the HVAC, you can see some meter 1, 2, 3, and 4 refer to the monitoring of the energy before and during the application, as well as the quality, which was on the right, made by some quality sensors that were tested and calibrated and validated against precision system in advance. And both were deployed, one inside and one outside the area close to the HVAC system. In terms of results, to summarize in simple words, we have achieved during the period of comparing 2 months before and the months during the application, around 14% of reduction in energy consumption. This, of course, was slightly lower than the 20% target, but that was also in conjunction with, at the end of the process, a maintenance system, which I'll explain at the end in the result, in the conclusion, what that was actually useful for. And in this slide, we can also see we have differentiated between different time and temperature and humidity, because, of course, this can have effect in terms of how much the HVAC system operates, consume. Usually for lower temperature, you have a higher consumption, so more benefit. As the higher temperature, we are talking the UK, about 25, 23 degrees. And also the number of events at that higher temperature were lower. So overall, also in terms of humidity, we have seen a benefit at the lower end and the higher end of the humidity, which is also what usually we expect in this environment and climate. The other results, of course, were in terms of air quality. So we have seen a reduction indoor of the NO2, PM2.5, but as well as a small reduction of the CO2. As we expected, the pollution was reduced, but also the CO2 was an important magic because that contributed to reducing the circulation and the change of air, which mainly inside the building is driven by CO2 levels, not by pollution usually. And in conclusion, so to summarize, I can say that the testing we have done have proven that the technology has been working, has provided a 14% reduction, in the same time air pollution removal and benefits. And this was also achieved just with an external unit. If we had the possibility to install internal unit, that would have a major effect because we have seen in other applications even 50 or 60% reduction inside buildings when applied. And finally, I mentioned before, the HVAC system was at the end of the testing was given a maintenance, but because we were monitoring the system as well, and we were able to re-switch on the APA system again, we have noticed a drastic reduction of energy consumption, which is associated, of course, with the maintenance and cleaning of the radiator and the heat pump. However, we have seen the consumption was stable during also the application of the APA system. As soon as we switched it off, the consumption started to gain the old numbers. And that means because the radiator and everything was starting to plug it down, up, and making the system overall less efficient. So this is actually another step that we have been testing recently, and there is more information we can give for the next conference with the interesting result of the combination of the system when also can prolong the benefit of a cleaning its implementation. And this is all I have to say, and thank you very much for your attention and the invitation. If you have any question, I'm happy to respond.
Thank you very much, Mr. Galatioto. Your presentation was short but quite informative. We are expecting to see new results of yours in later circumstances, in later days or months. I think there is no question from our chat box, but we thank you a lot. And for our participants, I would like to say that we are learning a lot being here. So we ask you to join us in session 4, which will start in about 15 minutes from now on. So hope to see you then. Bye-bye.
Thank you. Bye.